So really the only thing that you need to really remember with isotopes is that the number of protons is always the same, and the mass number is protons plus neutrons. And from there, you can kind of figure out all of the other information that's really relevant to that isotope. This is kind of an interesting periodic table because it kind of just think about all of these elements just kind of having been put on there at the same time. Either that or you just like never gave any thought to like when the periodic table was put together. Even in Chem 20, I don't really talk about it, right? But a lot of these elements, so some of them discovered before 1800, then 1800 to 1849, 1815 to 1899, adds a few in here. Or sorry, those are the purple ones, so gallium, germanium, indium, thallium. Yeah, pretty much all the noble gases. 100 to 1949, added some of these other ones in between. I believe that there's practically no non-man-made technetium. It was like a hole in the periodic table for a long time. It's just not very stable. And then these ones from 1915 to 2012, I believe are all man-made elements. So created in particle accelerators. And they only exist for fractions of a fraction of a second before they fall apart. Just not stable. If you didn't know also, this is how Dmitry Mendeleev completed the first periodic table. Not really, but putting together the periodic table is tricky. So in our modern periodic tables, our elements are listed increasing atomic number rather than increasing relative mass. There's not a lot of examples of things that don't increase in mass, but like the average mass of cobalt to nickel goes from 58.93 to 58.69. So, and then it starts to increase again in terms of average mass. And then this periodic table contains more than Mendeleev's because we've discovered more. So major divisions of the periodic table. This is going to be really important when we start to move towards nomenclature, because the nomenclature of different compounds is dependent on the types of really these major groups that get combined together. So everything that's sort of the light yellow beige color, maybe manila, those are all metals. Right, vast majority of the elements are actually metals. Then the next most common sort of group are the nonmetals. And then the smallest group are the metalloids. And the metalloids really just exist in the transition region between metals and nonmetals. So being able to know if something is a metal or a nonmetal is, again, very helpful for nomenclature. I think you could probably put together these definitions, at least for metals. Right? We're very familiar with metals. Again, most elements are metals. They're good conductors, they're malleable, ductile, often shiny, and they tend to lose electrons when they undergo chemical changes. Nonmetals are poor conductors, not ductile, not malleable, gain electrons when they undergo chemical changes, so pretty much the exact opposite of metals in just about every way. And then metalloids, of course, are weird, and they have properties of metals and properties of nonmetals. And then several of them are classified as semiconductors because they have intermediate and highly temperature dependent electrical conductivity. So the tablet that I'm using to project onto the screen, the projector, basically anything that you use that's an electronic device uses semiconductors because they end up being electronic gates that can be turned on and off at will. Very, very useful. In group transition elements, periods and groups. So a period on the periodic table is the row. So every row is a period. And then every group is the vertical column. So rows are periods, columns are groups. And then we also sort of divide these up into smaller groups of main group elements, transition elements. So main groups being here on the sides, and they really bracket the transition metals. And that has to do with the electron orbitals that are filled, the order that they're filled in, where the valence electrons are, which we'll cover later. Noble gases, which is group 8A, are mostly unreactive, which probably contributed to them taking a long time to discover. Because if it doesn't react with anything, how do you figure out that it is a thing, to put that as vaguely as possible? Right? If it doesn't react, then how do you identify it? Alkali metals, group 1A, are all reactive metals. So since I got two periodic tables, right, hydrogen and everything below that, all highly reactive metals. The alkali earth metals come next to group 1A. It's group 2A. So beryllium and everything below that. And I guess I should point this out too. It's one of those things I forget. There's sort of two different classifications for the groups. 1, it would just be group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on across. So that's everything on the periodic table, but we split the main group elements into sort of the A group. It's like 1A, 2A, and then we skip all the transition metals and start at 3A. So on this periodic table, they're in Roman numerals. I think in the book, it'll just say 1A, 2A, like the Arabic numerals. All right, so like 1A. So 2A, fairly reactive, and then halogens are very reactive nonmetals. So that's the last group, so fluorine and everything below that. This is always where I'm so tempted to just go into electrons, but...
What about lanthanides and actinides?
Oh yeah, lanthanides and actinides. Those are these guys down here, and we don't talk about them. We'll talk about them a little bit. I mean, the most interesting ones probably down here are things like uranium, which is used for nuclear fuel, also nuclear bombs. Yeah, things get weird. Actually, we will talk about those in this class, I think.
There's also a study, well, I said to have definitions for those on the study, so I was just curious.
Oh, okay. Yeah, the other thing about the periodic table that is worth mentioning, thank you for bringing these up, is these actually fit in here. So the periodic table would actually be like 14 elements longer than it already is, because these fit into this space. Of course, the reason that we don't put them into that space is because then the periodic table, this size, where you could see these, would be the length of the room, and that's very inconvenient. It happens to work out this way because of the way that electron orbitals fill. Again, it's just so much of the periodic table can be explained by talking about electron orbitals, but we're not talking about that yet. Talk about it later. We will talk about them just a little bit in terms of ions. So for ions losing or gaining electrons, now remember, this is key. For any given element, number of protons never changes. The protons are all the positive charges. So the only way that we can have ions is by changing the number of electrons. So you can either gain or lose electrons. And where that gets a little bit confusing is that electrons have negative charges. So when you add an electron, you get a more negative charge. And a lot of chemical reactions involve the exchange of these electrons. It explains why the halogens and the alkali metals and alkali earth metals are so reactive, because they really, really, really want to gain or lose 1 or 2 electrons. So if in one of our chemical changes we have a sodium atom, and it loses, well actually, look at this. It loses 1 electron. So what this sort of pseudo reaction is saying is that we have sodium, it undergoes a chemical change, it's the arrow, and after that chemical change, we have sodium with a positive 1 charge, and we have 1 electron. So we lost an electron from the sodium, and now we have a positive charge. For fluorine, now on this side we've got the opposite happening. We have fluorine, and it gains 1 electron in some chemical process to become fluoride, F-. So positively charged ions are called cations. Negatively charged anions are called anions. And then you always write the charge. This is something, if you had me for Chem 20, I wasn't a stickler about putting the charge first or second, but I'll be paying more attention to that in grading. So when you have a charge on an ion, so let's say we had something that had more than 1 charge, like calcium, that'd be Ca2+, not +2. If it is just the sign, then you can just put a plus or a minus. So I think we mentioned that main group metals tend to lose electrons, or actually metals in general tend to lose electrons, forming cation. And they'll form a cation. If they're a main group metal, they'll form a cation with the same number of electrons as the nearest noble gas. So for example, sodium, and you have to think about the periodic table as sort of wrapping around. So every time you get to the end of the row, it wraps around to the next period. At the end of the period, it wraps around to the next period. So sodium loses 1 electron to have the same number of electrons as neon. And actually, because let's break this down even more. Okay, so if sodium is neutral, how many electrons does it have? It'll have 11 electrons. Why does it have 11 electrons? Because it has 11 protons. So this was a question on the quiz. I'm going to just use We use P plus for protons. Right. Protons and electrons have opposite but equal charges. So protons are always plus, each proton is +1, every electron is -1. So sodium, when it's neutral, has 11 electrons, 11 protons, no charge. They cancel each other out. If it loses 1 electron, now it's Na plus. So how many electrons does it have? 10 electrons. And it still has 11 protons. So for neon, if neon has a neutral charge, how many electrons does it have? 10 electrons, because it has 10 protons. So when sodium's losing 1 electron, it gets the same number of electrons as neon. Same thing for magnesium, or similar thing for magnesium, I guess I should say. How many electrons is magnesium going to lose? 2, so that it can have the same as neon. All right, so for each of these alkali metals, group 1A, alkali earth metals, group 2A, they'll lose 1 or 2 electrons because that's how they get back to the nearest noble gas. Of course, we haven't talked about octets and valence electrons yet, but maybe, hopefully, you remember that from Chem 20. All right, so nonmetals, I guess it's on the slide, but if the goal of the alkali metals and alkali earth metals is to get to the same number of electrons as the nearest noble gas, what do you think fluorine does? Gain 1 electron. Just like in the example we had before, because fluorine has 9 electrons when it's neutral, 9 protons, but it wants to gain 1 electron to become F minus, because then it's got 10 electrons, 9 protons. That's the same for all of the halogens. And it's the same or similar for the chalcogens, is what these are called. We didn't mention those. But oxygen, sulfur, selenium, and maybe tellurium, they'll try to gain 2 electrons to get to the same as the nearest noble gas. So these guys go forward because that's closer than going all the way around backwards. All right, so sulfur, oxygen, selenium, they'll all form 2- charges because they need 2 electrons to have the same as the nearest noble gas. When we do get to, I don't know how much we'll go over it in this class, but we talk a little bit more about like why transition metals form some of the charges they do. I think I could show you for the ones that form consistent charges like scandium, silver, zinc, cadmium, aluminum, gallium, and indium. Those ones kind of make sense based on their valence electrons. So when we get to that, I'll talk about that. Talk about it more. You talk about it more in Chem 2. But most of the transition elements have more than one oxidation state, is what it's called. So they'll form more than one type of charge. Sometimes it's consistent. So like iron, primarily 2 and 3. Cobalt's primarily 2 and 3. Nickel's 2 and 3. Both positive charges, though. So 2 plus, 3 plus. So if there was a group to remember or memorize, it would be all of the ones that form those consistent charges. Again, looking forward to nomenclature. Okay, we talked about this. Right, so alkali metals, that's group 1A, so the first column, tendency to lose 1 electron to form 1 plus. 2A will lose 2 electrons to form 2 plus. Halogens will gain 1 electron to form 1 minus. And the oxygen family, I don't know if they avoid the word chalcogen, but they form 2- charges because they need 2 electrons to get to that noble gas electron configuration. Oh yeah, there's consistent charges. I'm going to add some in here actually. Gallium and indium, cadmium, silver, scandium. Those are just kind of useful ones to memorize. All right, so last one. Predict the charges of the monatomic ions formed by these main group elements. So what charge do you think nitrogen's going to form? Yeah. Why does it want to form a 3 minus? Because what?
3, 5, 8. The first 2, no.
The gains.
Yeah, like these. But it wants to gain 3 electrons to get to neon. Yeah. So yeah, nitrogen, 3 minus, and then rubidium. Yeah, I always get like rubidium, strontium, cesium, and barium. I could never remember if they're 1 or 2. I always have to look at a periodic table for those. But yeah, it'll be Well, a plus or 1 plus. Cool. So molar mass is how we count atoms because we can't count them individually. And so it's kind of like counting shrimp. How many of you guys have actually like gone to the store and bought shrimp before? I think like I've done it like once. So if you go and you buy shrimp, they sell them by the count. And so it's telling you about how many shrimp you get per pound. So 41 to 50 count shrimp means that you're going to get between 41 and 50 shrimp for every pound of shrimp that you buy. And so a smaller count means larger shrimp because it's still a pound of shrimp. So if you get like 10 or 15 count shrimp, then you're getting 10 or 15 giant shrimp, which is an oxymoron, in that pound, right? So like these tiger prawns, or I guess they're tiger prawns, they're not jumbo shrimp. I just like jumbo shrimp because it's an oxymoron. Big tiger prawns could be 10 to 15 count, where each shrimp could weigh as much as 1/10 of a pound. Which are some pretty big shrimp. Not so shrimpy shrimp. So shrimp can be counted by weighing them. It's easier than actually counting out individual shrimp. So if you had like 2 pounds of 41 to 50 count shrimp, you'd get anywhere from 82 to 100 shrimp, assuming you're not being cheated. A similar but more precise concept exists for atoms, and almost a more necessary concept. So often need to know the amount of atoms in a sample of a given mass because chemical processes happen between the individual particles. And if you go on to Chem 2, there are a lot of processes that really depend on the number of particles that are present because that determines things like rates and equilibrium. So at a real simple level, 2 hydrogen atoms combine with 1 oxygen atom to form 1 molecule of water. So you write this is like H2 plus O2. Well, actually, I'm going to just make this even simpler. 2H plus O gives you H2O. Right, so things are happening at an atomic level, and we're talking about these individual atoms. So if we want to know the number of atoms in anything of an ordinary size, even though these processes are happening at this atomic level, it's way more useful to do things at like a regular scale. So we count them by weighing rather than any other method. And it's similar to when we count large numbers of other objects. It's like a dozen donuts, a dozen eggs. That just means 12 eggs, 12 donuts, or 12 objects. It doesn't matter what the object is. You can count 12 of them and say that that's a dozen. Or you can count a gross, and a gross is 144 objects. So I don't know if I've ever had to buy a gross of something, but you can count things like that. Gross of Legos. So for chemistry, the chemist's dozen is the mole, which is abbreviated as MOL. And the mole is the amount of material containing 6.02214 times 10 to the 23 particles. And that's a stupid number. That number is too big to comprehend. We'll go over some things that sort of highlight that, some examples. This is also called Avogadro's number. So we could say 1 mole of anything. It would be nonsense, but we could say 1 mole of anything. So like 1 mole of pennies, or I guess you could say 22 pennies contains about 1 mole of copper atoms. Or a tablespoon of water contains approximately 1 mole of water molecules. And this is the thing that got cut out here. Where'd it go? Ah, yes. Because the abbreviation for mole is MOL instead of MOLE. So I'm getting close. The 3 minutes saved. Anyways. All right, so where did the mole come from? Why is it 6.022 times 10 to the 23, which is as far as I expect you to memorize it, 6.022. The value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. So 12 grams of carbon-12 is 1 mole of carbon atoms. And it's important that it's carbon-12. Again, we've got isotopes. So the mass on the periodic table is 12.01. Or if you go out farther, it's like 12.008 or 7, can't remember. That's accounting for other isotopes. When the mole, this number of the mole was invented, they said just carbon-12. So 12 grams of carbon-12 is exactly 1 mole of carbon atoms. So it gives us a relationship then, or conversion factor, between mass, really in terms of grams of carbon, and the number of atoms, which is Avogadro's number. So now we can say, just like with the shrimp, right? We know that 41 to 50 count of shrimp is 41 to 50 shrimp per pound. Here we're saying that it's 1 mole of atoms. So 6.022 times 10 to the 23 atoms per mole. And then we could say, if we use moles, we can convert that to grams. So we can convert between numbers of moles and number of atoms, similarly to how you would convert between dozens of eggs or a number of eggs. So 1 dozen eggs is 12 eggs. So for atoms, we just say 1 mole of atoms is 6.022 times 10 to the 23 atoms. And just like our other conversion factors, because those two, again, remember units give us agreed upon quantities for certain things. And so when we say that 1 mole is equal to 6.022 times 10 to the 23, those things are equivalent. And that means when we construct a conversion factor or a fraction out of them, whether the 1 is on top or on the bottom and the 6.022 times 10 to the 23 is on top or on bottom, doesn't matter. Both of those things technically equal 1. So we can flip this around. I think I missed wait, I think my slides got out of order. Before we move on, I wanted to talk about this, because I said a mole is a stupid number of things. So imagine this, you have 1 mole of pennies, so 6.022 times 10 to the 23 pennies, that would cover the entire Earth's surface to a depth of 300 meters. I mean, you imagine like 300 meters is like approximately 3 football fields. So you took 3 football fields in length, it would just be that deep in pennies everywhere. Across the oceans, everything would be just covered in pennies, 300 meters deep. I mean, you think of a grain of sand. A grain of sand, a tiny, tiny thing, but if you had 1 mole grains of sand, it would cover the entire state of Texas to a depth of several feet. You have to get a lot of sand. Oh, I did this. I don't remember what the number is, or how far you would actually get. I think it was something like 1 times 10 to the 10. So if you lived to be 80, and for every single second of your life, you were counting atoms at like 5 atoms per second or something, you would get to like 1 times 10 to the 10, which is not half of 1 times 10 to the 23. I can't even do the math right now. It's exponent, it's 10, right? It's 10 to the 10 times less. So you could not even in your entire life, if you counted 24 hours a day, you would not be able to get to 6.02 times 10 to the 23. So this is why we have to count atoms by the gram. Aside from the fact that we can't like see them individually. Stupid big number. Okay, let's go back to the math now. Yeah. Right, so it is just a conversion factor, and we're going to use it like that. So if a pure silver ring contains 2.8 times 10 to the 22 silver atoms, how many moles of silver atoms does it contain? I do realize the answer is on the slide, but give it a shot on your own. See if you get that answer, if you get that number. Made great progress last week, and then I realized also that there were a bunch of slides in here that needed to be moved to a different lecture, so more time to work on problems. Oh yeah, does anybody need a calculator rather than their phone? Uh-huh.
Take that number and multiply by 6.022 times 10 to the 23.
Did you get that answer? If that's what you're supposed to do, you should get that number. So we want to convert from atoms to moles. So what's the conversion factor? And really we can put in atoms or whatever there. So like this will give us 1 mole of atoms. Yeah, so you end up dividing by 6.022 times 10 to the 23. And this is where that E key really starts to come in handy. How many sig figs? 3. Or we could put it in scientific notation. Yeah, so when you're typing this into your calculator, I highly recommend that you just get used to using E whenever you have scientific notation. So this would be 2.80 E 22, because the E replaces the times 10 raised to something. And then you could put divided by 6.022 E 23. you'll run into problems if you do, let me do it in a different color. If you do 2.80 times 10 to the 22 divided by 6.022 times 10 to the 23, and you type that into your calculator like that, your calculator will do this part, and then your calculator will do this part, and then your calculator will multiply by 10 to the 23. So that's why the E key is really useful for scientific notation, because then your calculator treats it like a single number rather than another mathematical operation. So definitely if you're struggling to get the same numbers out of your calculator and there's scientific notation involved, let me know. We can figure out how you need to enter things. All right, so converting between mass and amount. So to count atoms by weighing them, we do need another conversion factor, because this just tells us how many atoms there are if we have a mole, or how many moles we have if we have an atom, but we need to get somewhere, need to somehow get to grams. And this is where that relationship to carbon-12 comes in handy, actually. So you may remember we defined the atomic mass unit also as the, what was it? It's based on carbon-12 again, but it's basically carbon-12 divided by 12. So that one proton or neutron is equal to 1/12 of carbon-12, which means that every proton or neutron is also then 1/12 of a gram, depending on the element. No, it's 1/12 of a gram. So the mass of 1 mole of atoms in an element is the molar mass. And we're going to be using molar masses a lot. So the element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. So all of these numbers on the periodic table here, we can use as molar masses. So if we have 1 mole of aluminum, that's going to be 26.98 grams. Aluminum, molar mass, 26.98. For carbon, this is using number off the periodic table, accounting for other isotopes, right? So 1 mole of carbon is going to be 12.01 grams. The number of decimal places you get there depends on the periodic table you use. Usually you get at least 2. And 1 mole of helium is 4.003 grams of helium. This again is kind of like those counts for shrimp. So if you have like 41 to 50 count, right, 41 to 50 shrimp per pound. But if you have 10 to 15 count, that's 10 to 15 shrimps per pound. So the shrimp are each a lot larger. This is a little bit flipped, because the larger the atomic mass, the more that 1 mole of atoms is going to weigh. So 1 mole of carbon or 1 mole of helium is a lot lighter than 1 mole of aluminum. And actually for lab later, I'll pull out the, well, I guess it's mostly related to density. I'll grab the mercury, which is surprisingly dense. So the molar mass of any element is the conversion factor between the mass in grams of that element and the amount in moles of that element. So it tells you how much 1 mole weighs. And again, just like with moles and 6.022 times 10 to the 23 atoms, those things are equivalent, so we can set them equal to 1 so that they can get 1 over the other, and we can invert that also. So here, 12.01 grams of carbon is 1 mole of carbon. So we can write this both as 12.01 over 1 mole or 1 over 12.01. Let me see here. Okay. So I'm going to do this one. And then the next one, let you guys work on your own for a bit. So if we want to calculate the amount of copper in moles in a 35.8 gram of pure copper sheet, the only thing that really matters here is that we have copper and that we have the mass of that copper sheet. Doesn't matter that it's a sheet, it's still made of pure copper. So our given is going to be 35.8 grams of copper. And it's important that you include copper as part of your units, especially when we get to stoichiometry. All right, so what else do we need?
So 1 mole of copper over 63.25 grams of copper.
Yeah, so 1 mole of copper is 63.55 grams of copper. I'm going to start doing the conversion factors like this. So this is the same as the multiplication that we were doing before. It's a little more compact. So since we want to cancel out grams of copper, when looking at this, we put the grams of copper on the bottom. So 63.55 grams of copper is 1 mole of copper. So we get 35.8. 35.8 divided by 63.55. So 0.56333 and so on. But we only have 3 sig figs, so it's 0.563 moles of copper. Conversion factors, yay.
Would you prefer a scientific notation, or can we leave it like that?
Usually if it's smaller than like 1/100th,
Okay.
so if it's smaller than like 0.01, then I guess, yeah, use scientific notation. You only need to use scientific, I'll say this, in terms of grading, sometimes scientific notation is required to have the correct number of sig figs, and then you have to use it. So if you end up with a really big number. Otherwise, you don't have to use scientific notation. All right, so we've got everything now that we need to count the number of atoms in a sample of an element by weighing it. So if you had a sample that you actually needed to weigh or figure out the number of atoms of, you would obtain the mass of that sample, then convert the mass to the amount of moles using that element's molar mass, and then convert the amount of moles to the number of atoms using Avogadro's number. And so your conceptual plan would look something like this. You start with the grams of the element, and then convert it to the moles of the element using molar mass. Then you convert it to the number of atoms using Avogadro's number. Like if you've taken Chem 20, you probably know this already, but in chemistry there are very, 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 very few just like set equations for anything. And that's partly because there's so many different molar masses, right? This is just like pure elements. Once we get into compounds, then you can have any combination of elements. And so the numbers that go into every equation change a little bit. But this is kind of the general outline for finding the number of atoms. All right, so how many carbon atoms are there in a 1.3 carat diamond? And then as a note, diamonds are made of carbon, crystalline carbon. And you're also given conversion factor. 1 carat equals 0.2 grams. All right, so how would you start this problem? Write out what you know. And that would be 1.3 carats.
We use the ratio of 0.20 grams of carbon over 1 carat.
Mm-hmm.
And then you're going to now do the ratio to the mole to the gram.
Mm-hmm.
And then you're going to do
Mm-hmm. Multiply across, divide by the bottom. Now, is there anything interesting about that number?
oh, carat. It's the same.
Well, carat is funny, but oh, you mean
The 1.3 and the 150 carat diamond, and the atom also is 1.3.
yeah. So, what if you typed in like started with 5 carats? Hmm.
I put in 13 carats.
Oh, and what did you get for your answer?
5.
5 carats? Yeah.
I got like 13.
Yeah. So if you, I didn't know this before. So the carat weight, there's two ways that it's done. One of them, so like 24 karat gold with a K, is 24 parts out of 24 parts. It's pure gold. Sometimes you'll have gold that has like copper mixed in. So like 18 karat gold, this is carat with a K, K-A-R-A-T, would be 18 parts gold out of every 24 parts of the metal. So copper might be mixed in something else, so it's cheaper, but also has different properties. Ah, shoot, I lost what I was going with. The carat with a C, Googled this. Yeah, it was on Merriam-Webster. Shoot, what was this? Yeah, it's just 0.2 grams, but it just so happens that, this is where I was going with it. You can use it for gold and you can use it for other things, and it's just 0.2 grams for every 1 carat. But when it comes to diamonds, it is actually roughly the number of atoms times 10 to the 22. So if you put in 13 carats, you'll get 1.3 times 10 to the 23. But you can make that 13 times 10 to the 22. So there's got to be some stuff canceling out there in kind of a spooky way. Anyways, thought that was interesting. Yeah, so we talked about this. Again, just try and wrap your head around just how much that is. too much. Right, okay, so we talked about molar masses for individual elements, and as I alluded to earlier, when we start combining elements to make compounds, we need to take into account all of the elements that are part of that compound. And that is the formula mass, which is the average mass of an individual molecule or formula unit if we're talking about ionic compounds. It can also be called the molecular mass or the molecular weight. And it's just the sum of the atoms in a single molecule or formula unit. So you take all of the parts that make up one molecule, one formula unit, and add them together. So what would the formula for calcium nitrate be? I know we haven't talked about nomenclature.
This is NO3.
Yeah, we'll talk more about nomenclature later. Nitrate by itself is NO3 minus, calcium is Ca2 plus. The charges, whenever you form, and this would be an ionic compound because it's made up of two ions. So when you have those two ions, their charges need to be balanced. So you need to have the same number of positive charges as you do negative charges. So this would be calcium nitrate. And I think the easiest way to go about this is write out all of the unique elements that are in this compound. So we have calcium, we have nitrogen, and we have oxygen. And then you write out how many of each there are. So how many calcium atoms are there? Just one. How many nitrogen atoms are there? Two. So when we have calcium nitrate written like this, these parentheses, just like in regular math, mean that the 2 here is, we're multiplying everything inside of those parentheses by 2. Because this is 1 calcium and there are 2 nitrate molecules associated with that. So we'll have 2 nitrogens and then how many oxygens? 6. And then we multiply the mass of each of those by its molar mass, or sorry, multiply the number of each of those by its molar mass. I'm going to use 2 decimal places on these because 1, that's what I have memorized, and 2, that's what's on this periodic table. So then you would get the masses of each of these. I guess I don't need to do that on my calculator. This will be 30, oh, not 32. 96. And then you add those together. One shorthand that I've used in the past. I'll show you 2 things here. So this will be 164.10 grams per mole of CaNO3 2. If you're doing this like on homework or something, if you have to show work, I'm totally okay with you using this shorthand. So you would write out still the masses, the number of each thing, but you can sort of summarize this whole getting the mass of each and then adding them together and just say that and then write 164.10 grams per mole. And that might be easier because when you want to type all of this into your calculator, instead of doing each thing individually and then typing in the first one plus the second one plus the third one in this case, you could type it in directly as 1 times, well, I guess you don't have to do the 1, but plus 2 times 14.01 plus 6 times 16.00, and that will equal this. It'll follow the correct order of operations because it'll do all of the multiplication first, then the addition, which is exactly what you want to do anyway. So faster to write that down than do everything else. And of course, don't take my word for it. Type it in. Make sure you get that. Yeah.
So if we're doing multiplication first, we have 4 sig figs, but then we have 5 sig figs to be rounded off to 4, and we keep it at 5.
Keep it at 5.
Keep it at 5.
Mm-hmm. Yeah, because we do that multiplication, but that keeps that number of sig figs. And then we keep the smallest number of decimal places. So there's like the one way that you can get more sig figs. Because it's, part of it is because you can be confident when you're adding big things together that that big number is good. And so the smaller numbers are all good. And so, yeah. Any questions about formula mass? Use the numbers on the periodic table. So for exams, I'll give you a periodic table on the exam, use the masses exactly as they are on that periodic table. So here we use 2 decimal places because this periodic table has 2 decimal places. On the exam, the periodic table will have, some of them might have 3, but just use whatever's on there because that's what I'm going to use for the key. And that's what I'll be looking for. Oh yeah, so the molar mass of a compound, the mass, which is the mass in grams of 1 mole of its molecules or formula units, is equivalent to its formula mass. So what would the molar mass of ammonia be? This is one of the weird ones. What's the formula for ammonia? Yeah, so ammonia is NH3. Ammonium is NH4 plus. So 1 nitrogen, 1 nitrogen, 3 hydrogens.
Ammonium is 18.05 grams per mole.
Yep. Yeah, so if it was ammonium, then it would be 18.05. It's just 1 more hydrogen. All right, so just like we were using molar mass for individual elements, we use that molar mass for molecules, and we count how many molecules there are for something. And again, just like we can say 1 dozen eggs and 1 dozen donuts, and both of those things mean 12 of those things, we can say 1 mole of atoms or 1 mole of molecules. The thing that changes that is the context. So if you're starting with a mass of molecules, and then you use Avogadro's number, going from the mass to moles to molecules, you end up with a number of individual molecules. If you start with atoms, then you'll get atoms out at the end. But it's all dependent on the context, because we're just counting things. I think this will be the last example that we do. So we'll give you some time to work on this. Okay. So how do we start this one?
Converting it to grams,
Yeah. 200
micrograms. Yeah. So 1 gram over 1,000 milligrams.
Yep, so I guess we're doing it the way that I was showing it, that it's, right, the prefix multiplier never goes with the, or the multiplier never goes with the prefix. So 1 milligram is 1 times 10 to the negative 3 grams. If you do 1,000 milligrams for 1 gram, it's the same thing.
And then 1 mole over 206.274 grams, that's the ratio for that.
You said it's 206 point.
206.274 grams.
Yep. So, all right, the other thing is that you have to calculate that. So you'd have carbon, hydrogen, oxygen, 13 carbons, 18 hydrogens, 2 oxygens, carbon times 12.01, hydrogen times 1.01, oxygen times 16.00. That'll give you that number, the molar mass of ibuprofen. And then because we've got moles.
2 times 10 to the 23rd over 1 mole.
Yep. And don't confuse molecules with moles. So 200 times 1e to the negative 3 times 6.022 e to the 23 divided by 206.274. Yep. So that's 5.8388 times 10 to the 20. And how many sig figs? 4. Or yon in Japanese.
Do you speak multiple languages?
No. I've been doing a little bit of Japanese on Duolingo, so I think I can count to 10 in Japanese for sure. I gotta keep up on my streak. I'm at 103 days. Any questions about molar masses, calculating the number of atoms or moles? Okay, so actually, ask a follow-up question to this. How many carbon atoms are there? How many carbon atoms are there in 200 milligrams of ibuprofen?
I feel like it's going to be wrong, because that's the wrong number for ibuprofen grams.
Oh, it depends on what you use to calculate it.
I did it 2 different ways, and it got the same number. I added them all together separately, and I put them together.
No, but I mean, did you use a different periodic table
What?
to get the 206.274?
I use
Use this one? Oh.
I got you.
Anyways, it matches what's up here, so it wasn't different enough to matter. Anyways, back to the question though. Yeah, how many carbon atoms? Not just 13 times Avogadro's number. 13 is right. So for every molecule of ibuprofen, there's 13 carbon atoms.
13 times the current.
Yeah, 13 times this. So if this is a number of molecules, then it's just going to be 13 times that, because every one of these molecules has 13. I think like the really, really large number makes it more confusing. I think it makes more sense, right, if I said it means how many carbon atoms are in one molecule of ibuprofen. Right, exactly the same thing that we did here. So if ibuprofen is C13H18O2, so if I have one ibuprofen, that's 13. If I had two ibuprofen, it'd be 26. If I have 100 ibuprofen, it'd be 1,030 or 1,300. So it's just whatever it is multiplied by 13. And then for hydrogen, multiplied by 18, oxygen multiplied by 2 for this particular molecule.